This is section 5.4, combining and decomposing functions. Okay, sums, products, and limiting values. Okay, we've seen limiting values before, so we'll be taking a look at them again. In fact, some of the stuff that's in this section we've actually already seen before. So we've seen functions before that look like a limiting value minus a temperature difference. We did this with the cup of hot cocoa being placed in a room. Okay, we didn't mention it at the time, but combining functions this way is actually very common in applications. So we're going to look at another similar example to this. And it's actually set up to already be a difference for you. So here's our setup. If a skydiver jumps from an airplane, the velocity v of the skydiver starts his fall with v equals 0 and increases toward terminal velocity. Terminal velocity depends on many factors, but for the average person in a normal position, it ranges between 117 and 125 miles per hour. Now, if the skydiver assumes what's called the bullet position, kind of like you've seen this in competition, it can be as high as 210 miles per hour. So if capital T is equal to terminal velocity, the difference between the skydiver's velocity and terminal velocity is an exponential function of time t. So the difference is the exponential function. So if d denotes a difference, then d is equal to t minus v, terminal velocity minus velocity of the skydiver. For this example, we'll assume that terminal velocity, the t, is 180 feet per second, which is about 123 miles per hour. Here are our questions. Number 1. What is the initial value of d? Question 2. 3 seconds after jumping out of the plane, the velocity is 75 feet per second. Find an exponential function for d. If necessary, round parameters to 3 places to the right of the decimal point. Question 3. Find a formula for v. If necessary, round parameters to 3 places to the right of the decimal point. Question 4. Express the velocity of the skydiver 6 seconds into the fall using functional notation. And question 5. Find the velocity of the skydiver 6 seconds into the fall, and if necessary, round or finally to the nearest whole number. Okay, so we're given terminal velocity capital T is 180, and we're told that when he jumps out of the plane, he starts with a velocity of 0. Okay, and then goes faster and faster from there. Okay, our solutions. Okay, number 1. We're given that t is equal to 180, and when the skydiver starts, v is equal to 0. So initially, d, remember that's t minus v. So initially, it's 180 minus 0, which is 180. So the initial value of d is 180 feet per second. Okay, question 2, we want to find a formula for d. Okay, we've already got the thing that's going to multiply the exponential part. We just have to find the base of the exponential. So we're given the velocity 3 seconds after the skydiver jumps from the plane is 75 feet per second. Okay, that's what's given in the problem. That 3 seconds after he jumps, he's traveling 75 feet per second. Notice it's 3 seconds later. So our delta t is 3. Okay, delta t is 3. Now remember, d is a difference between the terminal velocity of 180 and the velocity of the skydiver. So let's find the difference between 180 and 75. So 180 minus 75 is 105. Now when we were doing exponential regression, we had our little table. We're going to set up a table here. So I've got my t and my d. Now I have the t for for 2 values, 0 and 3 seconds later. Okay. Now this, remember, was the initial d, 180. And here is the d for 3 seconds. So I'm going to have 0, 180, and 3, 105. Okay, now we're told that this function d is supposed to be exponential. So I have to calculate the ratios of consecutive d values. Okay, again, because we're told that it's exponential. So I'm looking at 105 over 180. That's going to give me or get me started on my growth factor. Remember, I have a delta t of 3. So I look at 105 divided by 180. It's 0.58333 forever. Now remember, the delta t was 3. So the growth factor is going to be this ratio raised to the 1 over delta t power, so to the 1 over 3 power. So 0.58333 forever, raised to the 1/3, to 3 places, 0.836. There's our growth factor. And remember, we had the initial value of 180, so d is equal to 180 times 0.836 raised to the t power. There's our expression for d. Okay, question 3, you want to find a formula for v. Can you remember, in general, we had that d was equal to t minus v. Okay, we want to solve this for v. Remember, this is the initial relationship given in the problem. So I want to solve this for v. So I'm going to add v to both sides. So d plus v is equal to t. And since we're solving for v, subtract d. So v is equal to t minus d. Okay, now replace the values of t and d. Okay, t we're told is 180, and this up here is the expression for d, so v is equal to 180 minus 180 times 0.836 to the t power. There's your formula for v. Okay, question 4 was to find function notation for the velocity after 3 seconds. It's going to be v of 6. Remember, v is a function of time. It's going to be v of 6. Okay, question 5 actually makes us calculate v of 6. So we're going to have 180 minus 180 times 0.836 to the 6th power. Okay, so we're going to calculate v of 6. Okay, here's my calculator graphic. Okay, we're supposed to round this to the nearest whole number. So to the nearest whole number, 118.5 is going to be 119. So 119 feet per second. Composition of functions. This is a way to combine functions. It's a way we haven't seen before. So we look at a way of combining functions that is peculiar to functions. So without functions, we wouldn't have this operation of composition. So this is just kind of an operation like, addition, subtraction, multiplication, or operations for numbers. Composition is an operation for functions. So definition. Let f and g be two functions. Then the composition of f with g, and it's noted like this. You put a little open circle between the f and the g. It almost looks like you spelled the word fog. And it's read f composed of g. It's given by f composed of g of x is equal to f of g of x. So it's f of g of x. You evaluate a function at a function. That's what's going on here. Composition is evaluate a function at a function. Now, warning. In general, composition of functions does not commute. That means that in general, f composed of g does not equal g composed with f. Okay, we actually know of operations that don't commute. Division doesn't commute. 6 divided by 2 is not 2 divided by 6. Subtraction won't commute. 6 minus 2 is not 2 minus 6. In terms of our operations, the only operations that commute are addition and multiplication. So the fact that composition doesn't commute should not be all that alarming. Let's take a look at some examples. Okay, number 1 says let f of x equal 4x minus 9 and g of x equal 3x plus 11. Find the following. Simplify your answers. In part A, f composed of g of x. Part B, g composed of f of x. Okay, now in general, how difficult it is to do the composition comes down to how bad are the functions. Our functions aren't too bad. A linear function and another linear function. Our solutions. Okay, in part A, f composed of g of x by definition is f of g of x. This is simply its definition. Now, if we do what my dear Aunt Sally says, we're supposed to start from the innermost parentheses and work our way out. Okay, the innermost is technically just x, nothing we can do. As we work our way out, we encounter g of x. So the first thing we're going to do is we're going to replace g of x with what it is. Okay, so and g of x is 3x plus 11. So I'm going to replace this g of x with 3x plus 11. So I'm going to have f of 3x plus 11. And remember, this notation, f of 3x plus 11, means, in the formula for f, so back up here, replace x with 3x plus 11. So I'm going to replace this x right here with 3x plus 11. So I'm going to have 4 times 3x plus 11 minus 9. So again, what's in parentheses? That was playing the role of x in the formula for f. Now we're going to do the simplify part. So that means I have to distribute the 4. So I'll have 12x plus 44 minus 9. And we take a little bit further, we can do 44 minus 9, and that'll give us 12x plus 35. That's f composed with g of x. 12x plus 35. Okay, for part B, g composes f of x. By definition, it's g of f of x. That reads definition, g of f of x. Okay, now again, starting from the inside, the first thing we can do is replace f of x with what it is. So we're going to replace f of x with what it is. It's 4x minus 9. So I'm going to have g of 4x minus 9. Remember this notation, g of 4x minus 9 means a formula for g, so back up here, replace this x with 4x minus 9. So that x right there gets replaced with 4x minus 9. So I'll have 3 times 4x minus 9 plus 11. So again, this expression in parentheses, that was the original x in the formula for g. Okay, now distribute the 3. So I'll have 12x minus 27 plus 11. And now you can combine negative 27 plus 11 and have 12x minus 16. That's our formula for g composed with f of x, 12x minus 16. And do notice, they are different. Okay, they are different. That's to be expected, because in general, they're not the same. Now, typically, if the functions are kind of nasty, there's not a whole lot to do, because you can't really do anything with really nasty functions. So my example number 2, we'll let f of x equals 7x plus 13, and g of x will equal the square root of 2x minus 7. So find the following, simplify your answers. Part A, f composed with g of x. Part B, g composed with f of x. Okay, notice f is not too bad. G is kind of messy. So our solutions. For part A, f composed with g of x. Remember, by definition, it's f of g of x. Now, just like we did before, we replace g of x by what it is. G of x is the square root of 2x minus 7. So we're going to have f of the square root of 2x minus 7. Again, with this notation in the formula for f, so up here, replace x with the square root of 2x minus 7. So that x gets replaced with the square root of 2x minus 7. So I'll have 7 times the square root of 2x minus 7 plus 13. And that's all you can do. You cannot combine any further. The 13 is not under the square root. There's nothing else you can do. Okay, let's switch it. G composed with f of x. By definition, it's g of f of x. Okay, the first thing we're going to do is we're going to replace f of x with what it is. Okay, f of x is 7x plus 13. So I'll have g of 7x plus 13. Okay, now remember, this notation means in the formula for g, so right here, replace this x with 7x plus 13. So I'm going to replace this x with 7x plus 13. I'll have the square root of 2 times 7x plus 13 minus 7. Okay, now notice in this one, everything is under the radical. So I need to distribute the 2. So I'll have the square root of 14x plus 26 minus 7. Now again, because everything is under the radical, I need to do 26 minus 7. So I'll have the square root of 14x plus 9. Oh, I'm sorry, that should be 19, shouldn't it? So change that 9 to a 19. Let's see if we can do it now. So change that 9 to a 19. There, we fixed it. Okay. So this one was a little bit longer, but again, the two answers are different. Okay, let's have kind of a word problem thing. Number 3. The surface area S of a sphere is a function of its radius r. The function is given by S of r is equal to 4 pi r squared. That is the formula for the surface area of the sphere, of radius r. The radius of the sphere is increasing at a rate of 2 inches per second. Answer the following. Simplify your answers. Okay, number 1 says, express the radius r as a function of t, where t is equal to seconds since the radius began expanding. And B says, express the surface area S as a function of t. So notice, if r is a function of t and S is a function of r, then S is also a function of t. So we got S of r is 4 pi r squared, and we're going to have some sort of expression for r in terms of t. So our solutions. Okay, for part A, in t seconds, the radius will be 2t inches, because remember, we're increasing at a rate of 2 inches per second, kind of like distance is rate times time. So r is equal to 2t. So r of t is equal to 2t. There's r as a function of t. For part B, okay, S of t will be S of r of t. Okay, because remember, it's normally S of r, but here is r as a function of t. So I'm going to have, in my formula for S, replace r with r of t, which is 2t. So I'm going to have 4 pi times 2t squared. Okay, again, I just replaced r of t with 2t. Okay, and it's supposed to be squared according to the formula. Okay, this becomes 4t squared. So I have 4 pi times 4t squared. And you should do the 4 times 4. So I get 16 pi t squared. There's S as a function of t. Okay, our next topic, piecewise functions. Now sometimes the formula for a function is different for different values of the independent variable. So these are called the piecewise functions. So you have different formulas for different pieces of what would be called the domain in algebra. So definition. A piecewise function is a function that has more than one formula. That's all it is. It's a function that has more than one formula. Now that means that the formula is in pieces. The graph may or may not be in pieces. So even though there may be more than one formula for the function, the graph of the function may or may not be in pieces. Depends upon how nicely the pieces of the formula patch up with each other. So the classic example of a piecewise function is what's called the post office function. Okay, so the price of the first stamp changes depending upon the weight of the letter. Okay, and it just literally jumps up to the next price, so it's not a gradual thing. And the post office function will be our first example. So, graphing and evaluating piecewise functions on the calculator. Now, the TI-84, the newer models, are actually fairly good at drawing these piecewise functions. The 83s are not so good. In fact, sometimes with the 83, the graph just looks horrible. So, we're going to look at how to graph and evaluate piecewise functions on the calculator. Now, be warned that sometimes the graph can look strange, and that a hand-drawn graph may actually look better than what the calculator can draw. Kind of how do we give this to our calculator? We don't put it into several different y's. We put it all into one of the y's. So, some examples. Now, the first example is going to illustrate everything we need to know about feeding a piecewise function to the calculator. So, as of January 17th, 2016, the postage P in cents for a standard-sized first-class letter weighing W ounces is given by the following function. So P is equal to 41 cents if 0 is less than W is less than or equal to 1. Now, you can't have a 0 ounce letter. I mean, that's not a letter. It's 63 cents if 1 is less than W is less than or equal to 2. And it's 84 cents if 2 is less than W is less than or equal to 3. Okay, the post office, after, I think if you go past 3.5 ounces, they no longer consider it first class. Now, part A says, graph the function in an appropriate viewing window. Question B, use the calculator to find the first class postage for a letter that weighs 2.5 ounces. Notice, you can just look at it right here and say, oh, it's got to be 84 cents. But we want to see how do we make our calculator do it. Question C, use the calculator to find the first class postage for a letter that weighs 1.75 ounces. And notice you can see, oh, 1.75 ounces, so between those two guys, it's 63 cents. So doing these two by eyeballing the function is a lot quicker than feeding it to the calculator. But this is just so we can get used to the notation for piecewise function. This one is kind of simple enough to do it. You know, for an appropriate viewing window, remember, these are the Y values. The biggest one is 84, and you know, you can't have 0 cents, so it's like 0 to maybe something bigger than 84 might be appropriate. And then for the X's, which in this case are the W's, it goes from 0 out to 3, so you know, it's like the X values don't go out that far. So we're going to go through the details of how do we actually graph something like this. How do we graph a piecewise function? Now, these parts out here after the word if, those are called the restrictions or constraints on the independent variable, which in this case is W. So our solutions. Okay, in order to enter piecewise functions into the calculator as one function, so that is we're going to put it into Y1, we must obey the following restrictions. So restriction number 1. In the calculator, the restrictions on W, which are going to be restrictions on X in the calculator, multiply the formulas of the respective pieces. So again, going back up here to the function, we'd have this restriction times 41, this restriction times 63, this restriction times 84. Okay, it sounds weird, but that's what we got to do for the calculator. Restriction number 2. The calculator does not understand a three-sided inequality like 1 less than W less than or equal to 2. It doesn't understand that. We have to break it into two smaller inequalities joined by the word and. Okay, the calculator does have the word and as a function. Okay, it really does. You'll literally see the word and. Entering a piecewise function into the calculator is kind of a long, drawn-out process, and it's because of the limitations of the calculator. Okay, restriction number 3. Again, 1 less than W less than or equal to 2 is the same as this. 1 less than W and W less than or equal to 2. Okay, so this string of inequalities is this inequality and this one. Okay, again, notice my inequalities points to the same direction. Points to the left, points to the left, points to the left, points to the left. Okay, so now restriction number 3. Okay, now again, to continue this restriction here, I'm sorry. So with these two restrictions, we'll enter each piece of the function in the calculator like this. Okay, here is the first one. 41 cents times 0 less than W and W less than or equal to 1. That was the first one. Remember the second one? 63 times 1 less than W and W less than or equal to 2. And the last one was 84 times 2 less than W and W less than or equal to 3. Now, if the formula for the function were something instead of just simple numbers, say it was like 2x plus 3, I'd have to have 2x plus 3 in parentheses. So it's kind of like if the formula is more than just one simple expression, you enclose it in parentheses, just like we did with the restrictions in parentheses. Okay, restriction number 3. Since we want to have just one function and not 3 separate functions, we add the 3 above formulas. Okay, so we're going to add up each one of those. Each one of the pieces gets added in the Y1. So we're going to enter into the calculator because it's going to look like this. 41 times 0 less than w and w less than equal to 1 plus 63 times 1 less than w and w less than equal to 2 plus 84 times 2 less than w and w less than equal to 3. Notice it's long. Okay, it's very long, and this is just to get our calculator to understand it. Again, those are times signs, not x's. Now, you don't really need to do the times in your calculator. If you just put 41 in open parentheses, it understands it to be times. So that's kind of what we're going to enter into the calculator. Now, the question becomes, where do I find these inequality symbols and the word and in the calculator? Okay, so locating inequalities and the word and. Okay, in mathematics, the words and, or, and not are what are called logical connectives. All of the inequalities and logical connectives are located in the test menu. Okay, the test menu is accessed by pressing the second of math. So if you press second math, okay, so here's our calculator. Okay, there is math. Notice second is test. If we press it, there. Here are all the inequalities. Okay, equals, not equal, greater than equal to, less than equal to. Okay, the logic, scroll over, and, or, XOR. This is what's called the exclusive OR. And not. Notice not has a parenthesis, so it's like not something. And just joins two things, or joins two things. The difference between this OR and XOR is this is what's called the exclusive OR. This OR is what's called the inclusive OR. The inclusive OR allows for the possibility of both being true. The exclusive OR does not. It's kind of like in everyday language, we always think of it as the XOR. It's kind of like if someone asks you, is your sister pretty or does she look like you? So again, here is the test menu, and here are your tests. Does it equal? Does it not equal? Is it greater than equal to, less than equal to? And you can scroll over to logic. There, and, or, exclusive or, and not. We'll be using and. Okay, we're going to be using and. Okay, we're now ready to enter our function into y1. Okay, so this is going to be fun. Okay, let's go back to what it's supposed to look like. It's supposed to look like that. So let me take out the calculator. Oh, there it is. Let's quit that screen. Okay, I'm going to put it in y1. So let's see. Let me give myself some room. So y equal. Okay, 41 times, open parenthesis, 0. Then do second test. You want the less than, so choice 5. Less than x. Okay, and, so second test. Scroll over to logic. And x, you want the less than or equal to, so second test. Less than or equal to is choice 6. And that's 1. Close parenthesis. Plus, okay, now the middle formula. 63 times, open parenthesis, 1, second test, less than, choice 5, x, then and, so second test, logic, enter, and x, second test, less than or equal to, so choice 6, 2, close parenthesis, plus 84 times, again you don't need to say times, you can just do the open parenthesis, so open parenthesis, 2, second test, less than x, second test, logic, just press enter since it's on hand, x, second test, less than or equal to, choice 6, 3, close. And notice the earlier part that we entered in got kind of scrolled off, okay, but it's still there. So let me get caught up here. So, okay, that's what I can see, right? So if I take out my calculator here again, that's what I can see. Okay? So again, only the last bits of the formula are visible, so we hope and pray we got it right. So we're going to quit the screen, and this is what I use for my x. Okay, I use 0, 4, 1, and for y, the 0, 110. Okay, the 100 cents, I'm assuming up to $1. Okay, so let me go ahead and set my window. So window, okay, minimum of 0, maximum of 4, okay, scale of 1, minimum y is 0, maximum y is 100. These are cents, so 100 cents, that would be $1. And a scale of 10. Okay, and then we just graph. Okay, notice it's 3 line segments, 3 horizontal line segments. Okay. It looks like I have something there, but I don't think I do I? Let me be sure. I don't see anything. Just to be safe. Let's see if there's anything more in my y's. Nope, just y1. But it sure looks like there's a piece there, doesn't it? Okay, so if I get caught up here, yeah, it's there too, isn't it? Okay. So there's our graph. There's the answer to part A. Remember, question B was we're supposed to use our calculator to find the postage on 2.5 ounces. So if I do P of 2.5, which is really y1 of 2.5, okay, remember we already know what it is because we eyeballed the function, but just like any other function evaluation, so let me quit this. Vars, y vars, function, and y of 2.5, there. Okay, 84. Oh, I got my float set on 0, don't I? So let me mode. Let's float the float. Okay, let's quit that. And let's do it again. 84. Okay, and then if I do P of 1.75, which is really y1 of 1.75, 63 cents. Okay. So entering a piecewise function in the calculator is long and time consuming, but if you're going to have to evaluate something over and over, it might be worth it. So I have another example where the pieces are a little more complicated. After all, each one of these formulas was really just a number. So question 2. Given the function f of x equal to 2x plus 1 if 0 is less than x is less than or equal to 3, 1 minus x if 3 is less than x is less than or equal to 8, and 3 if x is greater than 8, graph the function in an appropriate viewing window. Find f of 3, f of 5, and f of 12. Okay, notice my minimum x is 0. My maximum, I can have x greater than 8. If you want to have the 0 to 10, that's fine. Okay, now for the y. Okay, try to figure out a maximum y. Evaluate each one of these pieces at each one of these numbers. Like if x is 0, that's 1, that's 1, that's 3. If x is 3, 2 times 3, 6 plus 7, that's 7, that's minus 2, and that's still 3. Okay. And if x is 8, 2 times 8 is 16, plus 1 is 17. So far that's the biggest. Okay, 1 minus 8, that's negative 7. So far that's the smallest. So it looks like minus 3 for a minimum of x or something smaller than that, and a 17 for a maximum. So, and for my function evaluations, b is f of 3, c is f of 5, and d is f of 12. Okay, let's see if we can do this into the calculator. So here are our solutions. Okay. So again, if I just go back to what the formula said, see if we can do it from the formula. Okay, so let me get out my calculator again, clear this nonsense out, clear out this y equal. Okay, so I'm looking at, open parenthesis, 2x plus 1, close parenthesis, times the restriction, 0, second test, less than, choice 5, x, and second test, and x, second test, less than or equal to, choice 6, 3, close parenthesis, plus the next formula, open parenthesis, 1 minus x, close parenthesis, times its restriction. 3. Second test. Choice 5 for less than. X. Second test. And X. Second test. Less than or equal to. Choice 6. Less than or equal to 8. Close parenthesis. Then plus the last piece. Plus 3. I don't need parentheses around it since it's just a number. Then times, open parenthesis, x, okay, greater than 8. Second test, greater than is choice number 3. Then 8, close it. Okay, now let's set up our window. Okay, again, let me get caught up here. Okay, for the window. Okay, the x-min can be 0. Okay, now, because part D makes us find f of 12, I should at least go out to 12. Okay, I chose 0 to 15. Okay, so now, for the y. Okay, now again, remember, part D was f of 12. That's why I had to go a little bit past 12. For the y, okay, when we evaluate each one of the functions, each piece of the function at those, what are called the endpoints, going back here. Okay, again, if x is 0, that's 1, that's 1, that's 3. If x is 3, that's 7, that's minus 2, that's 3. So far I have 7 for a max and minus 3 for a min. But if x is 8, see 16, that's 17, that's minus 7. So, going back here, okay, I did negative 10, 10, 1 for y, okay, so I probably should have gone with something bigger because of the 2x plus 1. So, here's my graph. Let me get the same window here. Window. 0, 15, 2. Okay, instead I'm doing negative 10 to 10. I really should, because of the 17, let me do minus 20 to 20. Let me change it. Minus 20, 20. Again, the reason I'm having them be the same but different in sign is to keep things in the middle. Okay, to keep things in the middle. To keep my origin in the middle. So now let's just graph away. I'm wondering, what did this look like? I'd had a different scale, that's why it looks more crowded. Okay, now, for f of 3, it's y1 of 3. So again, we've done this so many times before, hopefully you're sick of it. So vars, y vars, function, enter, of 3, and we get 7. Okay, and then let's see, part C was f of 5, so just do second enter, change the 3 to a 5. Here we get negative 4. Let me get caught up here. And the last one was f of 12. So if we do second enter, scroll back and change that to a 12, close parenthesis. We get the same thing, of course. Now again, the TI-83 may not make the graph look so nice. So you probably in class you might have to tell me that your graph is wigging out on you. Applications of piecewise functions. So the word problems, huh? So we're going to look at some applications of piecewise functions. We have a couple here. So some examples. Number 1 says, the local power company charges its residential customers for electricity during the months of June through September according to this table. So the monthly kilowatt hours, and here's your monthly charge. So if your kilowatt hours are between 0 to 650, it's 760 plus 0.046 cents per kilowatt hour. And there for 650 to 1,000, 3855 plus 0.07838 per kilowatt hour above 650. And more than 1,000, it's 6585 plus 0.08186 per kilowatt hour above 1,000. So part A, write the piecewise function for the cost C of x that gives the monthly charge for electricity for a residential customer that uses x kilowatt hours of electricity during one of the months in question. Question B, find the charge for electricity for a customer that uses 1,720 kilowatt hours electricity during the month of July. Round your function to the nearest whole cent. And question C, find the charge for electricity for a customer that uses 835 kilowatt hours of electricity during the month of July. And again, round to find for the nearest whole cent. So once we get our function, we'll evaluate y1 of 20 and y1 of 835. Okay, now if you're really swift, you can almost write the function from the table. Let's see if we're really that swift. Okay. Let me clear this out. Let me clear out my y1. Okay. Okay, the first one is 0 to 650. Okay, and it's going to be 760, so whoops, open parenthesis. 7.60 plus 0.0466. Okay, times the kilowatt hours. Remember, that's x. And that gets multiplied by its restriction. Its restriction is you're between 0 and 650. Okay, in case you're wondering, can we actually write it as a three-sided inequality? Okay, this is what's going to happen. Okay, so 0, okay, second test, less than or equal to, okay, our x, which is then less than or equal to 650, just so you'll see what happens. 650. Okay, suppose we have that, and just to make it complete, let's just say plus 0, just to make it complete. Then second, quit this, just so you can see what happens. Vars, y vars, let's try to evaluate 500, because 500 is between 0 and 650. Now again, the 83s don't understand it. The 84s might. Okay, oh, it actually understood it, didn't it? Maybe we can do that. Let's try and see. So y equals, okay, I'm going to try to enter all of them as three-sided inequalities. Those that have the 83, see if it'll do it. I know mine doesn't. That's why I've been separating into two. So not plus 0, but plus, open parenthesis. Okay, this time I'm doing 3855, 38.55, plus, okay, 0.0738, 0.07838. Now that's times the kilowatt hours above 650. Okay, the kilowatt hours above 650 is x minus 650. So open parenthesis, x minus 650. Those are the kilowatt hours above 650. Okay, close for the x minus 650, then close for the restriction. I got something weird here. I have to go back and correct that. That decimal point shouldn't be there, right? It's 0.07838. Okay, then let's see, two closing parentheses. No, okay, I didn't close my last one, did I? Then plus. Okay, did I do times my restriction? I don't think I did I? No, I didn't. So let me go back and do my times my restriction. So times my restriction, I'm between 650 and 1,000, right? So 650, second test, less than, okay, choice number 5, x, second test, less than or equal to 1,000. So 6 less than or equal to 1,000, close, then plus, okay, this money, 65.85, 65.85 plus 0.08186. Okay, then that's times the kilowatt hours above 1,000. Okay, the kilowatt hours above 1,000 is x minus 1,000. So x minus 1,000. Close that. Close one for the formula, and then times its restriction. Its restriction is more than 1,000. So x second test greater than, choice 3, 1,000. Okay, hopefully I have everything. And we'll quit that. Okay, now to go through the details here, let me get caught up to where we are. So here are our details. Okay, so our solutions. Okay, for part A, the restrictions for x. Okay, 0 is less equal to x less equal to 650 with a price of 7.60 plus 0.0466x. Okay, 650 less than x less than or equal to 1,000 with a price of 3855 plus 0.07838 times kilowatt hours over 650. Now again, kilowatt hours over 650 is x minus 650, because notice if x is 700 kilowatt hours, 700 minus 650, you have 50 above that. Okay, the next one was x greater than 1,000. Again, that should be x less than or equal to 1,000. Okay, so x less than 1,000, which is the way we entered it. With a price of 65.85 plus, I don't know why I have a t there, plus 0.085186 times kilowatt hours over 1,000. Remember, kilowatt hours over 1,000 is x minus 1,000. Okay, so there's our formula. Okay. Okay. There's our piecewise function. So that's the answer to part A. That's our piecewise function. Now I've already entered it into the calculator. Okay, now when I did this on the slide, I did not enter into the calculator. I actually did it by hand. So I'm claiming it's quicker to evaluate parts B and C by hand. Okay, C of 1720. Okay, 1720 is more than 1,000. So I'm going to use the bottom formula. 65.85 plus 0.0816 times 1720 minus 1,000. You have 65.85 plus 0.08186 times 720. Okay, to the nearest whole cent, $124.79. Since I have my calculator, let me see if I entered it in right. So vars, y vars, function. Okay, 1720, right? Wow, I must have something wrong, right? I have no idea why I would have wrong. Probably never be able to find it either. But I must have something wrong in my function. I wonder if it's done writing the three-sided inequalities like that it doesn't understand it. Okay, it's the greater than 1,000 part that's doing it right. 65.85 plus 0.8186 times x minus 1,000 times x greater than 1,000, right? Guess we'll never find it. And then for part C, we were looking for 835 kilowatt hours. So C of 835, you're between 650 and 1,000, so you'd use the middle formula, right? Going back, you'd be using this one. 3855 plus 0.07838 times your 835 minus 650. So 38.55 times 0.07838 times 185. And to the nearest whole cent, $53.05. I wonder if the calculator will get this one right. Because again, I'm wondering what did I key in wrong. So let's see. Quit. Second enter. Change the 1720 to 835. 835. Delete that 0. Well, that one's wrong too. I'm wondering now. Well, I guess after I do this, I might check to see what I did wrong. Oh, our last one. Okay, one simplified tax reform plan has proposed the following taxation rules. For individuals whose income does not exceed $20,000, their tax would be 5% of their income. For individuals whose income exceeds $20,000 but does not exceed $250,000, their tax would be $1,000 plus 10% of any amount over $20,000. For individuals whose income exceeds $250,000, their tax would be $24,000 plus 15% of any amount over $250,000. So it says write a piecewise function. Oh, no tax on negative, right? So write a piecewise function capital T of X, that gives the tax for an individual that making X dollars. And part B, find the tax for an individual that makes $85,000 per year. Notice, since we're only doing one function evaluation, it's not really worth the effort to put this into the calculator because we're only doing one function evaluation. And notice the $85,000, it would be using this middle formula right here. Because $85,000 is, you're exceeding $20,000, but you have not exceeded $250,000. Notice under this tax plan there are no such things as deductions. So our solutions. Okay, let's figure out the restrictions. Okay, I've got you do not exceed 20,000. Okay, remember, no taxes on negatives. So 0 less than or equal to X less than 20,000 with a tax of 5% of your income. Remember, your income is X, and 5% would be 0.05. Okay, then the next restriction. You exceed 20,000, but you do not exceed 250,000. So 20,000 less than X, which is less than 250,000. And your tax is 1,000 plus 10% of any amount over 20,000. Now the amount over 20,000 is X minus 20,000. Okay, that's your amount over 20,000. X minus 20,000. Whoops, something just dropped. Okay, and then the last one. Your income exceeds 250,000. So X would be greater than 250. X is greater than 250,000, and your tax is 24,000 plus 15% of the amount over 250,000. Now, over 250,000 is X minus 250,000. Okay? And now we just put all this together. Now remember, you're going to convert all your percents to decimals. So 0.05, 0.10, 0.15. Okay, we're calling it T of X. So our function, capital T of X is 0.05X. If 0 is less than X is less than 20,000, again, that's that very first restriction. Okay, and then 1,000 plus 0.10 times X minus 20,000, right? Okay, 1,000 plus 0.10 times X minus 20,000. If you're between 20,000 and 250,000. And lastly, the 24,000 plus 0.15, the 15%, times X minus 250,000 if X is greater than 250,000. Okay, so there's the tax function. And then question B was, what's the tax on $85,000? Okay, now 85,000, it's the middle formula. Okay, so we're going to have 1,000 plus 0.10 times 85,000 minus 25,000. Excuse me, 20,000. So 1,000 plus 0.10 times 65,000. So when you crunch this out, okay, you don't need to round or anything. It comes out to be nice whole dollars. $7,500. That's the end of section 5.4.